So for number 2, we're given the theorem of linear algebra that states if A and B are invertible matrices, then the product AB is invertible. And so for item A, it's asking us to outline a proof by contraposition. So basically, the contrapositive is we switch P and Q, and we deny both of them. So what we have to do is let's identify P. So in item A, P is going to be if A and B are invertible matrices, that's our P, and our Q is going to be then the product AB is invertible, right? And so we begin by assuming not Q. So we're going to say A, assume product AB is not invertible. Then we would develop our proof, and then we would show that it leads to not P. So A is not invertible. We're doing the opposite of A and B are invertible matrices. So A is not invertible, or B is not invertible. And to get the denial, when we have two propositions, we want to do not, say, proposition R and S. This is just going to be not R or not S. So it can be that either one of them are going to be false. So that's why we say A is not invertible or B is not invertible instead of saying A and B are not invertible. So we've assumed not Q shows that it leads to not P, and so our conclusion is going to be, therefore, if A and B are invertible matrices, then product AB is invertible. And so that is it for item A. Assume not Q, show that it leads to not P, therefore if P, then Q. So now let's do item B. And item B, it wants outline a proof of the converse of the theorem by contraposition. So the converse is going to be if Q, then P, right? So the contrapositive in this case, the contra, I'll just say it's contra, is going to be if not P, then not Q. So it's like we switch the order here in which they come. So P is going to go first, and then Q, and then we deny it, right? So we're going to begin assuming not P. So because P is the one in yellow, so for A, assume A is not invertible, or B is not invertible. We would develop it and show that it leads to not Q. So product AB is not invertible. And then we would then state the conclusion, right? Therefore, if Q, then P. So therefore, if we're going to say if product AB is invertible, then P, right? Then matrices A and B are invertible. Okay, so that was the contrapositive of the converse. Now we're going to go to item C. Wow, my handwriting is pretty terrible, but hopefully it makes sense to you guys. So item C, we want a proof of the theorem by contradiction. So the way that contradiction works is, so if we're going to go to contradiction, assume that we want to prove, say, proposition R. So we first assume not R, so we assume the opposite, assume not R, show that it leads to proposition T and not T, which is a contradiction, right? You can't have both T and not T. And so because the hypothesis leads to a contradiction, it means that the hypothesis was false. So this is what we're going to do. So assume that, so for C, we're going to assume the opposite of this. So remember that the opposite of a conditional, it's false when P is true and not Q. It's only when these conditions, when you meet these conditions, is that the conditional becomes false. So let A and B be invertible matrices. And suppose that product AB is not invertible. AB is not invertible. So we assume P and not Q, then we would develop it and show that it leads to proposition T. It's just a random proposition. Then we would develop it, show that it leads to not T, and then we would say T and not T, which is a contradiction, is a contradiction. So the conclusion would be, therefore, we're going to say if A, B are invertible, then so is product AB. Product AB. Okay. So basically, like we said, we begin by assuming that the conditional is false, and then we show that this leads to some contradiction. So that is it for item C. Now, what about the item D? So item D, we're going to outline a proof of the converse. So the converse is if Q, then P, but we're going to do it by contradiction, right? So in the case of the converse, this is going to be false if Q and not P. That is when the converse is going to be false. So we're going to say, okay, for D, assume Q, so assume product AB is invertible, and A is not invertible, or B is not invertible. So we begin by assuming Q and not P, then we would develop it, show that it leads to T, develop it, shows that it leads to not T, develop it, and then say, actually, we don't need to develop anymore. Then we would say that T and not T, so hypothesis is false, right? Is false. And then we would say, therefore, if Q, then P. Therefore, if product A, B is invertible, so is A and B. So that is it for item D. And lastly, for item E, we are going to do, let's see, a two-part proof that if A and B are invertible matrices, if and only if product AB is invertible. Okay, so now we're going to the biconditional. So the biconditional, and let me write this in. So the biconditional is of this form, biconditional. Biconditional, okay. It's of the form, if P implies Q, we have to show this, and Q implies P. So first we would do the proof of the conditional and then the proof of the converse. So what we're going to say here is, for item A, assume the conditional. So, assume P, right, and show that Q follows. So assume A and B are invertible matrices. Then we would develop it and show that Q follows. So A, B is invertible. And I'm not writing product AB just to save some time, but you guys can see the general structure. So we assume P, show that Q necessarily follows. Now we have to assume Q and show that P follows. Then we would say assume AB is invertible. Then we would develop it and then show that P necessarily follows. So we say, so A and B are invertible. And so our conclusion would be, therefore, A and B are invertible if and only if AB is as well. So this is basically assuming P and showing that Q follows, and then assuming Q and showing that P follows. And if we show that the conditional and the converse are true, then the biconditional is true as well.